Hello everyone, welcome to another episode of Deep Dive Knowledge Talk. Hello everyone! Let's dive into the fascinating intersection of generative AI and molecular design. Could you explain the significance of using a transformer-based model for generating molecules, especially in the context of achieving desired physical properties?
Using a transformer-based model for generating molecules is like teaching a robot to be a chef who can whip up new recipes based on the ingredients and flavors you want. In this case, the ingredients are the specific physical properties we want in the molecules, like how they might react, their strength, or their ability to dissolve in water. Transformers are powerful because they can learn from examples, similar to how a chef learns by tasting different dishes. They analyze a lot of data about existing molecules and their properties, which helps them understand how certain combinations of atoms can lead to the desired results. This understanding enables the model to generate new molecular structures, which are like unique recipes that meet those specific property requirements. Just like a chef can experiment with different ingredients to create a new dish, the transformer can combine various molecular components in creative and unexpected ways, potentially leading to innovations in drug discovery, materials science, and more. This approach opens the door to finding new molecules that might not have been obvious just from looking at what already exists.
That's a great analogy. Could you elaborate on the specific architecture used in this transformer model, particularly the role of the feed-forward artificial neural network, an encoder for molecular properties, and how it integrates with the transformer decoder for SMILES notation?
The architecture of this transformer model is like a two-part machine designed to create new molecular recipes based on specific property. In the first part, we have a feed-forward artificial neural network, an encoder that takes the desired physical properties as input. You can think of this encoder as a factory that takes raw materials, the physical properties, and processes them into a form that the machine can work with. Since the properties are not arranged in any particular order, we can't use the normal method that transformers typically use for sequencing. Instead, the feed-forward AN takes these properties and organizes them so the transformer can understand. It effectively transforms these properties into a format that highlights the important features related to creating molecular structure. The second part of the model is the decoder, which works with SMILES notation. Imagine the decoder as a skilled artist who can take the processed information from the factory, encoded properties, and create a beautiful painting, the molecular structure, based on that information. The decoder treats SMILES as a sequence, allowing it to generate the molecular structure, step by step. Together, the encoder and decoder work like a team. The encoder prepares the ingredients and the decoder crafts them into a finished dish. The decoder also goes through several rounds of improvement, like an artist refining their painting, to ensure the generated molecules are not only valid, but also truly reflect the desired property. This collaboration between the two parts of the model is key to generating molecules that meet specific criteria effectively.
That provides a clear picture of the model's architecture. Now, could you discuss the implementation of this model in PyTorch and how it facilitates customization and optimization for specific challenges in molecular chemistry, such as drug discovery?
Implementing this transformer model in PyTorch is like using a versatile toolkit to build and customize a machine that can create new molecular recipes. PyTorch provides a flexible framework that allows researchers to easily adapt the model for their specific needs in molecular chemistry, such as drug discovery. The customization comes from the ability to alter the model's architecture, training data, and optimization methods. For instance, while the basic structure of the model is in place, researchers can tweak the encoder and decoder layers, change how the data is processed, or adjust the way they define the desired physical property. This is similar to a chef adjusting a recipe based on available ingredients or personal taste preferences. When it comes to drug discovery, this model can generate potential drug candidates tailored for specific targets, like proteins or genes linked to diseases. After these candidates are created, researchers can use further computational methods, like molecular dynamic simulation, to see how these candidates would behave in real biological settings. This step is like testing a new dish in a restaurant to see if customers enjoy it. By combining the transformer model's creative capabilities with these advanced computational techniques, researchers can refine and select the most promising drug candidate. However, the effectiveness of the model is influenced by the quality and amount of data available for training. If there are gaps in the data, it can limit how well the model performs, just as a chef might struggle to create a dish without enough ingredients. Overall, PyTorch's implementation allows for a hands-on, iterative process where researchers can continually improve their molecular design efforts, paving the way for exciting advancements in drug discovery and other areas of molecular chemistry.
That analogy really captures the iterative nature of research and development. Can you explain some of the potential challenges or limitations faced when using this transformer model for generating molecules, particularly in relation to data quality and the complexity of molecular properties?
When using this transformer model for generating molecules, several challenges and limitations can arise, particularly concerning data quality and the complexities of molecular properties. One of the main issues is that the model often relies on the quality and comprehensiveness of the training data. If the data consists mostly of simpler molecules, the model tends to favor generating those simpler structures rather than more complex ones. This is like a painter who only practices with basic shapes. They may struggle to create intricate masterpieces because they haven't practiced with them enough. For example, when the target molecule has multiple chiral centers, which are specific arrangements of atoms, the model might generate a simpler, non-chiral molecule instead. This oversimplification occurs because the model has learned patterns based on what it has seen during training, leading to a bias towards common, simpler structures. Another challenge lies in how well the specified input properties relate to the actual molecular structures produced. While the generated molecules might exhibit the desired physical properties, they may not match the specific target molecules that researchers aim for. This situation is akin to someone trying to bake a cake with specific flavors, but ending up with a different dessert that still tastes good. It suggests that the model might be successfully learning to adhere to property constraints, but it could miss the mark on accurately representing the intended molecular structure. Furthermore, the model faces difficulties with stereochemistry and the generation of complex molecular structures. For instance, while it can produce valid Smile strings, the notation used to represent molecules, it may not capture specific stereochemical configurations accurately. This means that the model might generate simpler structures that do not fully represent the complexity of the intended target molecule. Overall, these challenges highlight the need for high-quality, diverse training data and the necessity to refine the model further to improve its ability to generate complex and accurate molecular structures. Without addressing these limitations, the effectiveness of the model in applications like drug discovery may be compromised.
Those insights into the challenges faced by the model are incredibly valuable. To wrap up our discussion, could you share the broader significance of this research in terms of its potential impact on fields like drug discovery and materials science? What does the future hold for transformer models in molecular design?
The research into transformer models for molecular design holds significant promise, particularly in the fields of drug discovery and materials science. By leveraging deep learning models, researchers can generate potential drug candidates tailored for specific biological targets, such as proteins, genes, or RNA molecules related to diseases. This approach is akin to having a powerful tool that helps scientists brainstorm new ideas that can lead to effective treatments. Once these potential drug candidates are generated, they can be tested and refined using computational methods. These methods provide valuable insights into key properties, such as the stability of molecules and how they bind to their target. This is essential because understanding how a drug will behave in a real biological environment can dramatically improve the chances of successful treatment outcomes. But it allows researchers to refine their selections, moving closer to discovering effective pharmaceuticals. Looking to the future, the integration of transformer models in molecular design is likely to grow. As data quality improves and models become more sophisticated, we can expect to see even more innovative compounds being developed. Additionally, these models can potentially streamline the design process, reducing the time and costs associated with drug discovery, which is often lengthy and expensive. Moreover, the applications of these models extend beyond just drug discovery. In materials science, for example, they could help in creating new materials with specific properties for various industries, from electronics to sustainable energy solutions. In summary, the broad significance of this research lies in its potential to expedite breakthroughs in healthcare and materials development, ultimately leading to improved treatments and innovative solutions to complex problems. As transformer models continue to evolve and adapt, their impact on molecular design in various scientific fields is likely to be profound and transformative.
Thank you, everyone, for joining us today. We've explored the exciting applications of transformer-based models in molecular design, where these powerful models are employed to generate new molecules with desired properties. As we've discussed, these models are implemented in PyTorch, providing flexibility and optimization for specific molecular chemistry challenges. Their success heavily relies on the quality and comprehensiveness of training data. While they excel in generating novel molecular structures, they still face challenges in creating complex structures and accurately depicting stereochemistry. However, their potential in drug discovery and materials science is undeniable, enabling the generation and refinement of drug candidates and materials with tailored properties. As data quality improves and models become more sophisticated, the impact of transformer models in these fields is poised to grow exponentially. We thank our esteemed guest for sharing their insights and inspiring us with the possibilities of these transformative technologies.